Yeah. So, hi everyone. Welcome to another session of the Bangalore Theory Seminar. Today, we are excited to have Meena Mahajan as a speaker today. And so, Meena is a senior professor at the Institute of Mathematical Sciences, Chennai. She did her bachelor's and master's in computer science from the Indian Institute of Technology, Bombay, and went on to do her PhD from the Indian Institute of Technology, Madras, under the supervision of Dr. Kamla Krithivishan. So, her research interests lie in the area of complexity theory, including proof complexity, as we'll see today, algebraic complexity, and circuit complexity. Her research interests also include combinatorics, discrete algorithms, and to paraphrase from a web page, anything that catches her fancy. So, she has been an ACM India eminent speaker since 2019. Was elected as a fellow to the Indian Academy of Sciences and has been awarded the J.C. Bose National Fellowship by the SERB DST. She has also been profiled in Vigyan Vidushi, 75 Women Trailblazers of Science, a resource book on the profiles of 75 Indian women scientists published by the DST Vigyan Prasa in 2023. With this, I'll hand it over to you.
Thank you. Thank you very much for that introduction. Yeah, I'm happy to be here giving a talk in IISc after many years. And this is about a topic that I've been working on in the last few years, proof complexity. It brings together proof complexity and algebraic complexity, two areas that I'm interested in. And the work that I'm going to talk about now is joint work with Yogesh Dahiya, who was my PhD student. He has now finished. He is a postdoc at IISc. Shashank Mouli, who did his PhD in the US, is now on the faculty at IIT Indore. He came visiting IISc, and that's when we got together and did this work. So I'm going to directly start with the problem statement, the problem setting, and then maybe a little later in the talk come to why we are looking at such a problem. So kind of changing the order a little bit. So the first thing can we hide that little, do I hide it from here? Because it's going to keep, no. It will be nice if we can hide it now, because it's not crucial, but it will hide a little bit of every title.
Yeah.
Or
Move it. Okay. Can you bring it down?
maybe bring it absolute bottom.
Bottom here.
Yeah,
This
perfect. Good. Yeah, thank you. Okay, so we want to, here's the problem setting. This is not the setting that we are interested in, but to start off. Suppose I give you a set of polynomials. It's a system of polynomial equations. And I claim that the system is satisfiable, meaning there is some point at which simultaneously all these polynomials become zero. So the system of polynomials has a common zero. Okay? And so I claim that the system has a common zero. I have to prove it to you. It's going to be very easy to give such a proof. All I have to do is to describe what that common zero is. So a proof that this system is satisfiable is simply the common zero. Verifying the proof means that if you are the person who's going to verify the proof, you just have to evaluate all these polynomials at that point. And what would be the cost of verifying that the proof is correct? You need to evaluate the polynomials, of course. So the cost of the field operations, how they are going to be implemented, and also it depends on how the polynomials are presented. So let's assume that the field is rationals, or maybe the field, some fixed finite field. The operations are not overly complicated. And let's assume that the polynomials are given in the most naive brute force way possible, explicitly as a sum of monomials. For each monomial, what is the coefficient? So then the cost of evaluating these polynomials is not going to be too much in terms of the size of the system of polynomials itself. So a proof is easy to describe, and a proof is also easy to verify. So a proof of the fact that this system of polynomials has a common zero. Now let's change the question to certifying unsatisfiability. I give you a system of polynomial equations, and I claim that there is no common zero. Okay? Again, I'm claiming this, and you are asking for a proof. How am I going to prove this to you? So it turns out that to prove that there is no So if there is a system of if a system of polynomials does have a common zero, then no matter what multipliers I give you, so the system of polynomials is f1, f2 to fn, and no matter what multiplier polynomials g1 to gm I give you, f1 g1 plus f2 g2 plus up to fn gm, this can never become identically 1, because in particular evaluated at the common zero, the left hand side is going to be 0. So there is no way that 1 can be generated through a combination of the f's. In other words, 1 is not in the ideal generated by these polynomials. So we can take this as a contrapositive to try and prove that there is no common zero. If there is a common zero, 1 is not in the ideal. Therefore, if 1 is in the ideal of generated by these polynomials, then that certifies unsatisfiability. All I mean by ideal is any polynomial which can be expressed in this form. Okay? So the ideal generated by f1 to fm is combinations like this. So these are not linear combinations, but combinations with polynomial multipliers. So this is what I would call this is a format in which I can give you a proof of unsatisfiability. So let's call this a proof system. And the fact that I've written out here says that this proof system is sound. If my proof of unsatisfiability consists of showing that 1 is in the ideal, it will never happen that I can give you a proof even though there is a common zero. Okay? So this is what soundness demands, that you should not be able to prove things that are false. So a proof which shows that the membership of 1 in this ideal is going to be a sound proof. But it's not enough for the proof system to be sound. So a proof system is, I have not formally introduced the term and I'm not going to, but it's a format in which we are going to describe proofs. We would like it to be sound. It should not end up proving false things. We would also like it to be complete. Every statement which is true should be provable in that system. Every statement of a particular type. So here the only types of statements we want to prove are statements of the type this system does not have a common zero. And it turns out that indeed this system is also complete. Whenever a system of polynomials has no common zero, indeed we can find these multipliers, some multipliers g1 to gn, such that this combination f1 g1 up to fn gn added together, they give 1. This is exactly the statement of Hilbert's Nullstellensatz. It tells us that you will always be able to find such a. So in other words, whenever there is no common zero, 1 is actually in that. So this is a complete proof system. For every system of polynomials of this form, there is a proof. And whenever there is a proof, the proof is the statement is indeed true. So put together, these two conditions give us a sound and complete method of certifying that a system of polynomials has no common zero. Having a common zero is relatively easy to certify. So this should remind you of essentially the difference between NP and co-NP, right? So the NP part, where it is easy to give witnesses, give the common zero. The co-NP part, you want to show that there is no common zero. In this case, we have to give these the proof of membership in this ideal. So we won't expect this task to be as easy. And indeed, this task is related to the NP co-NP problem. So let's move over to that. Before we do that, maybe we should also ask these questions which we asked for the satisfiability thing. How complicated is it to verify the proof? So in the case of no common zeros, the proof is that 1 is present in the ideal. One way to show that 1 is in the ideal is to present all those multipliers. But then one should again ask, how are those multipliers presented? Are they given as sums of monomials? Are they given as a circuit representation? All this could make a big difference to how easy or hard it is to verify. So we're going to assume that the multipliers are listed out explicitly as sums of monomials. So a proof is going to be a list of polynomials like this, satisfying this identity. That's the size of the proof is going to be the number of monomials into 1 to gm put together. The cost of verifying this proof would be that you would want to multiply out all of this and check whether it adds up to 1. Check that all the coefficients of all the other monomials cancel out. This is not necessarily going to be a very easy task. You can see that this already looks like a polynomial identity testing question, but in a very limited setting. The limited setting is that the f's are given to us explicitly, the g's are also given to us explicitly. So this is an easy instance of the polynomial identity test. But maybe instead of trying to verify this equation, I could do something else. I could show how 1 is in the ideal by deriving it line by line. Instead of giving you at one shot this entire proof, I can, which would be what I call a Hilbert's Nullstellensatz proof. I can prove to you that 1 is in the ideal by saying, look, each of these initial polynomials is in the ideal by definition. Okay? Now, whenever h, a polynomial h is in the ideal, so is the polynomial x times h, because this is the multiplier. Whenever two polynomials h and h prime are in the ideal, any linear combination of them is also in the ideal. You can just add them together because in the ideal, that's what we are allowed to. So if I use only these steps, starting from the fi's, and I finally end up deriving the polynomial 1, that is a proof that 1 is in the ideal. So this is the line by line derivation. So you can think of these as two different styles of proof. This is a completely static proof. I give you everything at one shot and then you sit and verify. Here also, maybe I give you everything at one shot, but you can verify one step at a time. And this makes a difference.
X and
A and B are field elements and X is a variable. So so in general, I will use things like X, Y, Z for variables, A, B, C for field constants. So if this were also a field element, it would be subsumed by this. So I can, if H is in the ideal, then H multiplied by some monomial, some variables is also in the ideal. So I can multiply it by a variable. And to keep things simple, I will multiply by one variable at a time, just so that you can do a step-by-step verification more easily. We'd want the degrees also to be small if possible. It may not always be possible. Yeah, but even more, so we would want the degrees to be small. The most crucial cost here is how many monomials do you have? So if the degree is small, the number of monomials will also be small, but it's not necessarily true the other way. Yeah, I guess I think my next slide should talk about, not next, one slide after that should talk about the cost of verifying. So now I come to why we are looking at such polynomial equations. I mean, if you're already doing algebraic complexity, I think this is a fairly natural thing to do. You wouldn't ask this question, why are we doing this? But even if you're not doing algebraic complexity, I think unsatisfiability of CNF formula. I mean, satisfiability is the canonical NP-complete problem that we start off with. It's certainly an interesting thing to look at. How would you certify unsatisfiability? Satisfiability, you just give the satisfying assignment and somebody checks that all the clauses are satisfied. So I'm assuming that the formula is in conjunctive normal form. This is not necessary for NP completeness, but it's convenient. And in this setting, that's what we will deal with. So now, for CNF formulas, satisfiability is in NP, unsatisfiability is in co-NP, and I'm rewriting certifying unsatisfiability using algebra. That's what we're doing here. So we're going to represent every variable as a polynomial. The variable x, the literal x in the CNF formula, I will encode as 1 minus x. The literal negation of x, I will encode as x. So if the variable x takes the value 1, satisfying a clause, a unit clause which has just x, this polynomial takes the value 0. So a polynomial becoming 0 is our stand-in substitute or metaphor for satisfiability. Okay, that's why negation x is replaced by x. And now if I have a clause which says at least one of these literals is true, I just multiply the encodings of all the literals in it. So if even one literal here is true, the corresponding polynomial is going to be 0 and then the product goes to 0. So we're just replacing truth, falseness in logical formulas by 0, non-zero in the algebraic world. But 0, non-zero gives us a much larger range to work with. No, you have so many non-zero values, and that's something that we hope to use. So clauses now are being encoded as these kinds of generalized monomials. Right? This is not exactly a monomial because you have a 1 minus x. But if I think of 1 minus x as a pseudo variable, x is a variable and 1 minus x is another variable. Let me call it x bar. Then the encoding of any clause is just a product of variables and pseudo variables. It's just one monomial. And that's what I call a generalized monomial, or a junta, it's called in some settings, if it's a small clause. Now, for every 0-1 assignment, alpha, if alpha satisfies the clause, then the encoding of the clause at that assignment is 0. If alpha falsifies the clause, the encoding of the clause at alpha is 1. So the encodings of these clauses on Boolean values are 0 and 1. At other values, they can take any values from whatever field we are working. Now, what if I have a CNF form? So this is what we do for a variable or a literal. This is what I do for a clause. And now I have a formula, which is a bunch of clauses. For each clause, I write down one polynomial. And the polynomial corresponding to a clause is this generalized monomial. And now I just ask, is there a common 0 for all of these? The common 0 would be an assignment that satisfies all the clauses. But now this question is not very well posed because there may be a common 0 which is not a 0-1 assignment. I'm only interested in 0-1 assignments. So really speaking, I would like to say that there is no, to certify the unsatisfiability of the CNF formula, I would like to say that there is no common zero which corresponds to a 0-1 setting. And there could be common zeros elsewhere in the field. I don't care about that. However, as it turns out, if f is unsat, then 1 is in this ideal, and if f is satisfiable, 1 is not in this ideal. No common Boolean 0 implies if and only if no common 0. This is something that we can show given the way we have encoded this. So the question of certifying unsatisfiability of a normal formula, we have transformed it into this question of certifying that there is no common 0 of a system of polynomials. And now this certification we want to do in an algebraic setting, hoping to use other stuff from algebra that was not available if you think of it only as a logical form. So the field can change depending on what you're working with. And for the same CNF formula over different fields, the cost of certifying unsatisfiability could be radically different. Yes. Yes, this is independent of the field.
Because of the encoding.
It's because of the encoding. Yes. So as long as the field has a 0 and a 1, that's all we need for this to go through. Okay, so now we are going to work with other fields, with many different kinds of fields, finite, infinite, and it's convenient to add these Boolean axioms. So I have this set of polynomials, and I add some more polynomials. Polynomials of the form xi square minus xi must be 0. Okay? Xi square minus xi must be 0. Well, over any field, this has only two solutions, 0 and 1. As far as I know, I don't know about extension fields. I think for all the fields that I have encountered, the only solutions for this are 0 and 1. Okay. So when I add these axioms also, so I'm going to call these axioms. So now my system of polynomial equations is all these polynomials corresponding to the initial clauses and all these polynomials, one for each variable. Now again, if there is no common 0 to the original system, there is no common 0 even when I throw in this. But now there are going to be multilinear witnessing polynomials. So remember, we said that if there is no common Boolean 0, then there is no common 0. If there is no common 0, then we know that there are these multipliers which come from the Hilbert's Nullstellensatz, which you will multiply with your initial f's to get 1 to prove that 1 is in the ideal. Those multipliers need not be multilinear. However, the moment I add the Boolean axioms, I can now talk about multilinear witnessing polynomials. So it's convenient to add these. So a multilinear polynomial is a polynomial in which each monomial has, for every variable, either the variable is absent or it is present with degree 1. So you can have x, y, z, you can have x, w, you cannot have x square 1. In each monomial, each variable has degree at most 1. Okay? So it's not linear, but multilinear in each variable. So notice that these initial polynomials that are encoding the CNF formula, they are multilinear. So I'm assuming that my clause never has a repeated literal. Why would you even deal with a, I mean, if your clause looks like x or x, then its encoding will not be multilinear. But you never write a clause which has repeated variables. No? So the initial encodings will all be multilinear. The Boolean axioms are not multilinear. But what the Boolean axioms do is to say that if I give you a polynomial which has an x square y term, well, I know that I have to work in this ideal. In this ideal, x square is the same as x because x square minus x is 0. So I can change x square y to xy. There is a process of doing it in that step-by-step derivation that we talked about, and x square y will become xy. So essentially, everything can be multilinearized. So we will almost always work assuming the Boolean axioms. We will often also add dual variables and dual axioms. This is, I already mentioned earlier that for x, instead of saying 1 minus x, I'll talk about a pseudo variable x bar. And then that x bar had better be the opposite of x. So I have these dual axioms, x plus xi, x plus x bar should be equal to 1. And this is actually quite important, though it's a very small trick. It's important because otherwise, if I look at the explicit representation of all my polynomials, an explicit representation here could be very big. No? If I have 1 minus x1 into 1 minus x2 into, let's say I have a clause of width n, and I write down its encoding, I multiply out to get all the monomials, there are 2 raised to n monomials suddenly. You don't even have time to write down the whole polynomial. But by using these kind of dual variables and dual axioms, we can ensure that every initial encoding of a clause is a single monomial. It's a generalized, that's why I had this word generalized here, because I intend to use these twin variables. Now each clause encoding is a single monomial.
There has to be a catch, right? Because somehow, like, so far the story is that the co-NP problem seems to have a small certificate.
No, I've not said that it has a small certificate. We are only talking about what kinds of things would be certificates. But we have still not reached the question of how big the certificates are. Okay, so coming back to certifying unsatisfiability of CNF formulas, we'll fix a field depending on what we want to do. And we will always assume that we have the Boolean axioms, we will have the dual axioms, and now we can encode any CNF formula. So a formula which is in CNF form, conjunctive normal form, is unsatisfiable if and only if one is in the ideal generated by the encodings of these initial clauses using, and I can prove that one is in the ideal by deriving it explicitly using those two rules that I mentioned earlier. From H, you are allowed to derive X times H. But X times H modulo the Boolean or dual axioms. So if H is a polynomial in which there are some monomials which already have X, when I multiply it by X, an X square term comes in. I change that X square to X because I'm working modulo B. Similarly, in H, maybe there is a monomial which has X bar. X into X bar is always going to be 0 because of our dual axiom. So that monomial you can remove. So from H, I can derive XH modulo this in one step, let's assume. Similarly, from H and H bar, I can take this linear combination and then again go modulo the Boolean dual axioms and derive this. And in this process, I want to derive one. So this is the proof system which is called polynomial calculus with resolution over the field F. So it's the polynomial calculus because you're calculating line by line and eventually reaching one, with resolution because we're using dual variables. Without the dual variables, it would be just polynomial calculus. And it's over the field F, that is part of the definition of the system, because for different Fs, these proof systems behave very differently. You do. So if you start with 3 CNFs, your initial clauses are all small. But along the way, there may still be a blow up, which perhaps could be controlled better if you have dual. So the most obvious reason why you would need it is because of the initial clauses, but even along the way, it can. Okay, so now this is the definition of the proof system itself. I hope the proof system definition is clear. So, but again, like I said, I'm not formally defining a proof system, but what I mean is a format in which you can write proofs of statements of a particular type. The statements we are considering is these polynomials do not have a common zero. And now the format of the proof is specified by these rules. The field is fixed and you're allowed to use these rules. And what is the size of a proof? A proof of unsatisfiability. And this is going to be the total number of monomials in all the lines. Remember, we are doing this line by line. We're not doing the Hilbert Nullstellensatz kind of thing where I give you all the multipliers and ask you to check. Line by line, I'm showing you, okay, this is how you proceed. And eventually you reach one. So at each line, you should be able to do the operation which is required. Right? So you should be able to, from H, you can multiply by X and then you have to go modulo this. You have to do this combination and go modulo BDI. And the cost of doing this is going to depend on how many monomials there are in H. So I will assume that each polynomial at every line in the proof is explicitly given as a sum of all the coefficients of the monomials are given explicitly. So therefore, that is the proof size, the total number of monomials in all the lines. So for now, I'm completely ignoring bit size. For instance, if my field were rationals, then a coefficient of 2 is very different from a coefficient of 2.000 multiple zeros followed by a 1. You know, the precision, the size required to write down this coefficient. So I'm just assuming that every coefficient requires 1 unit space for one size. So we're just counting how many coefficients do you need to write. Okay, so what do we demand from a proof system? It should be sound. It should never be the case that a satisfiable formula has a proof of unsatisfiability. We demand that the proof system is complete. Every unsatisfiable formula must have a proof of unsatisfiability. And as Siddharth asked earlier, we don't expect proofs to be short, no matter which field you choose. If every unsatisfiable formula F has some poly-sized PCR proof, then it would imply that NP is equal to co-NP. Of course, there are some minor caveats here, like what about a field operation cost and so on, but those are really minor. Morally, really, if in any PCRF system for any field F, if you are able to show that unsatisfiability can always be certified efficiently, then you have proven that NP is equal to 4. We don't expect this to happen. Therefore, we expect that no matter what field you pick, there must be some system of equations. There must be some CNF formula which is hard to prove then. Okay? So now this is what we are trying to do. Okay? So now I come to the real question that we are addressing, which is how do you prove lower bounds? We fully expect that there will be lower bounds, because if there are no lower bounds, it would be a breakthrough. How do we prove? So proving a lower bound in PCRF for any F does not imply that NP is not equal to 4. But proving the absence of a lower bound implies that NP is equal to 4. So this is a weaker goal. At least you should be able to show that PCRF does have lower bounds. And that's what we want to do.
Like the G1s that came through Hilbert's.
Nullstellensatz.
Yeah. So those I can't like convert it into a PCA. That is
No. So every Hilbert Nullstellensatz proof gives rise to a PCR proof, because line by line I have to generate. I have F1 to Fm. I generate F1 into G1. How do I do that? F1 into the first monomial of G1, F1 into the second monomial, and so on, and then add them.
Yeah.
So therefore, this tells us that if you can give lower bounds, it means that those Nullstellensatz certificates must be having large monomial size. So we know that there is always a Nullstellensatz certificate, but that certificate may require large size. It may just require too many monomials in the polynomials in order to derive one. Okay. So what kind of CNF formulas? Let's go back to CNF. What kind of CNF formulas are hard in which kind of systems? Many lower bounds are already known for various kinds of PCR. For instance, this is a formula which encodes the handshake, the negation of the handshake formula. Okay? For a graph G, the formula and a subset of the vertices, the formula F is encoding some subgraph of this graph defined as G prime B E prime. For every vertex in V, the degree of B in this subgraph is odd exactly when B is in S. And now if the size of S is odd, then obviously this formula is going to be unsatisfied. So this formula is a formula in what variables? The variables are going to tell you what do I put in E prime. So for every edge in the graph, I'm going to have a variable. I can set it to 0 or 1. If I set it to 1, means I'm picking it in E prime. If I set it to 0, I'm throwing it out. So those are my variables. And now this I would like to encode in CNF. That can also be done. But the CNF encoding itself may be large, but if G is of small degree, in particular if it's constant degree, the CNF encoding is not too large. If G is also an expander, then we can prove that certifying this formula is hard for the polynomial calculus. Okay? So it requires exponential size. But here now you can see where one dependence of the field comes in. The exponential size is only going to be if the field is of characteristic not equal to. Over characteristic 2, there is this odd, it very quickly vanishes and you can get trivially some very unsound kind of actions. So this is one example of a formula which is easy to describe. There is I give you a graph which is of constant degree, which has some kind of expansion property. Small enough sets have many neighbors. That's what I mean by expansion. And I give you a subset which is of odd size. And I say that this graph has a subgraph in which exactly those those vertices are of odd degree. We know that no such graph exists. And we want to prove that. We write this as a CNF formula, and then it can be proved that PCR proofs will be of exponential size. In the typo in the title, searching for PCR. Okay. So we saw one example where the PCR proofs are large. They're not always large. Some formulas, there are short PCR proofs. So maybe one may want a process of searching for a PCR proof, hoping to quickly show that, yes, this formula is unsatisfiable. We may not be able to do it all the time, but for many formulas, maybe we can do this. So how would we search for a proof? Well, again, this was something that came up earlier. The degree of a proof is the maximum degree of any polynomial that appears anywhere in that proof. And a PCR proof of degree D is going to have a derivation of size roughly n to the order D, where n is the number of variables. Okay? And in fact, you can even find such a proof. Suppose I know that this formula is unsatisfiable, and I also know, because somebody has told me, that there is a PCR proof of degree D. Then I have an algorithm which will do some kind of not quite brute force search, a slightly cleverer search, and find the proof of size n to the order d in time which is proportional to the n to the order d. Now, n to the order d may not necessarily be very efficient, but it's not too bad either. It can be found with some combination of Gaussian elimination and iterative basis expansion, or there are these so-called Grosvenor basis algorithms. So some such variant can eventually work to find it. If I tell you that there is a PCR proof of small degree, then there is some way of finding it, not super efficiently, maybe not polynomial time, but quasi-polynomial time, certainly better than exponential. So therefore, it may be reasonable to conclude this, that a small degree proof implies that there is a not too large size proof, because you're finding the proof in that much time, so that proof cannot be too large. So we would like to make this a little bit more precise. In what sense does a small degree proof imply a not too large size proof? And this is made precise in, by these fairly old results, Clegg, Edmonds, Impagliazzo, Pudlak, and Zal. What they showed is this statement up here. If I have a system of n-variate polynomials, which is unsatisfiable, all the initial polynomials are of degree at most d0. And if I have a PCR proof of size, let's say small s, okay, then I can convert it to possibly a different PCR proof, which is of small degree. And what do I mean by small degree? Its degree is going to be order d0, that is a starting degree plus square root of n log s. In other words, if you can rewrite this in this form. Okay. So the degree that is required to actually prove unsatisfiability here satisfies this relation. If S is the smallest size and D is the smallest degree, then we have this kind of a relation. Remember, the smallest size proof and the smallest degree proof may be completely different. It's not that the same proof is achieving small size and small degree. I may have one proof which achieves small size but uses large degree, and I have another proof which achieves small degree. Of course, if it's small degree, it cannot be too large, but it could be larger than this. So this is just telling us how to go from that it is possible to go from one to the other. So what this tells us is that if your starting degree is small, so in particular when we started with 3 cm, the starting degree would be 3. Okay. So if my starting degree is small, then this is essentially d square. Okay. So if I'm able to show that any PCR proof must require degree omega n here, then this is going to become n square by n. Omega n log s is omega n. S has to be exponential size. So this is our technique for proving size lower bounds. We are really interested in size lower bounds. How big is the proof? That's proof complexity. But in order to prove the size lower bound, okay, the primary tool is to show a degree lower because of this relation.
So this does not go from back from PCR to the G1 through Gn. It's just still saying that you can give me an alternate PCR proof with a trade-off between the size.
So what is the difference between a PCR proof and a Nullstellensatz? So every Nullstellensatz proof is also a PCR proof. A PCR, the difference between the two is more conceptual, that a Nullstellensatz proof expects you to give the proof of membership of one in the ideal explicitly. And in PCR, you're building it up line by line. The fact that you can build up things line by line allows you to do things more efficiently. So probably we know there are formulas for which there is no small Nullstellensatz proof, but there are small PCR proofs. So in some sense, this is similar to what you would see as the difference between, let's say, a truth table representation of a function. Say I have a Boolean function and I say, give it to me explicitly. So write down its values at all possible settings. Give me the entire truth table, or give me a circuit which computes the same function, a Boolean circuit with and or not. That circuit could be much smaller than the truth. So that is very similar to what is happening here. In the polynomial calculus, with or without resolution, you are allowed to build up these witnesses, and you are allowed to reuse earlier. You can compute smaller, some part of G1 and some part of G2 are common. You don't compute it twice in PCR. You compute it once and then use it in both places. So using this fact, we can actually show, and this is well known, separations between PC and Nullstellensatz. So Nullstellensatz, for Nullstellensatz also, the primary tool for size lower bounds is through degree. If the degree is large, then the size will have to be large. For PCR also, that is the main tool. Okay, so I still haven't yet come to what we have done, but now here I've come to one of the settings that I would like to describe. So if the characteristic of the field is not 2, then Boolean values, okay, you don't Yeah, sorry.
Last result holds for any S or S. S.
Size S?
Yes. Is there a relation between S and M or like
No, so this is the relation.
any S?
So if S is very small, that is, you can very easily certify unsatisfiability. What's going to happen is something over here also will become trivial. So Boolean values we encoded as 0, 1. But if some of you have seen analysis of Boolean functions, for instance, we often encode it as -1, 1 also. It doesn't have to be 0, 1. It can be minus. As long as you have two different non-zero values, one is standing for 0 and one is standing for true and one is standing for false. We're trying to encode logical truth and logical falseness, and we need two different values for them. So we could have used plus minus 1. And I mean, then you can just say that, okay, I will encode the variable x as 1 plus xi by 2 and negation x as 1 minus xi by 2 or vice versa. And then I should change the Boolean ideal. Instead of saying that x square is equal to x, which forces x to be 0, 1, I should say x square is equal to 1. This forces x to be plus 1 or minus 1. Over any field, x square equals 1 has only two roots, right? Plus 1 and minus. So this is just a change of basis. And the change of basis for the variables is an affine translation. So it's not going to change the degree of the proof. If I choose to encode my original CNF using this basis, and if my original CNF somehow I had shown that there was a degree lower bound, it will hold even in this basis. If I had shown that there is a degree upper bound, then that will also hold in this basis. Nothing changes with respect to degree. But on the other hand, with respect to size, things can dramatically change. Because you can see this 1 plus x, right? So if I just have a monomial x, y, z, now suddenly it becomes 1 plus x into 1 plus y into 1 plus z. Boom. From one monomial, I've got 8 monomials. Exactly what we tried to tackle by introducing those dual variables, that advantage has gone now if you do this. So the size can dramatically change. In fact, that size degree relation that was there on the previous slide, it breaks completely. And what do I mean by break is not that the proof of that thing holds. The statement itself is not true. Degree is no longer representative of size. And why is this happening? The main reason is that setting a variable in the 0, 1 setting a variable to 0 kills the monomial. Here, you set a variable to either plus 1 or minus 1. The rest of the monomial is still there. You can't wish a monomial away by setting one variable. So there's no easy way to get rid of many monomials. And that means there's no easy way to prune down the size. On the other hand, if you are working in the plus 1, minus 1 setting, multiplication by x can be inverted. You multiply by x and then you multiply again by x, the x square has gone away because x square is 1. There was no analog of this in the 0, 1 setting. So in some sense, there are strange things that happen here, which are very different from the 0, 1 encoding. And this is not something that we are used to thinking about when we think of complexity of Boolean functions. Boolean functions, what difference does it make 0, 1, minus 1, 1? But here, we are talking about how large is the proof and things change completely. PCR lower bounds are not robust to even such a small change in basis. How are you going to get lower bounds when I'm doing the encoding over plus 1, minus 1? If I can't get lower bounds here, then that says that, okay, to prove unsatisfiability, I should work over plus 1, minus 1. But of course, even over plus 1, minus 1, we expect that there will be lower bounds. I mean, just the fact that we changed the basis should not alter the fact that we believe NP is not equal to coefficient. So there will be lower bounds even in this basis. How are we going to prove them? Our primary tool till now was size degree relation, and that has gone. There must be some other tool. So in fact, there was no other tool till fairly recently.
But you can probably just start with a reverse engineer a polynomial like other lower bound, the other basis. Like, so, right? Like, pick up, okay. Point is, you have to start with a CNF and not a polynomial.
Even if you start with the polynomial, things are not easy. But if you want to start with the CNF, things are even harder. In particular, I gave one example of a CNF formula which was hard, which was something that violated the handshake lemma.
Yeah.
That the polynomials encoding that are super easy in the plus 1, minus 1. So in terms of size of a proof, those formulas have small proofs. So even though we started with something which was hard there, it does not translate to something hard. So the question is, how are we going to get lower bounds over this basis? So in fact, let me introduce yet another proof system, sum of squares. Okay. which some of you may have heard of because sum of squares ties in very nicely to various kinds of optimization approximation algorithms. But in the proof complexity setting, this is what I mean by it. So I'm not, this works only over reals or rationals or basically over an ordered field. Not any ordered, I keep over reals and rationals, over nothing else. Okay, so we change the encoding. I'll encode it as x, not as 1 minus x. Negation x is encoded as 1 minus x or as a dual variable. And a clause, instead of encoding it as a polynomial equation, which should become 0, I encode it as an inequality. So this is the main change. I don't insist that some polynomial should go to 0. I insist that some polynomial should go to a positive value. So the encodings of these literals should be positive. If I sum up all these encodings and say at least one literal should be true, therefore this should be positive. But of course, the Boolean dual axioms I have, no, x square should be equal to x. If I'm looking at 0, 1 or x square should be equal to 1 and so on. Those have to be equations. So I just encode them as two inequalities. Okay. And now what does a proof look like? I have a system of inequalities and my inequalities are like this. F1 is greater than or equal to 0, F2 is Fm is greater. They're all inequalities. This has no common 0 provided there are multipliers like this. Okay. And each of these multipliers is guaranteed to be non-negative. That's all I require, that it should be guaranteed to be non-negative. So if each of these multipliers is guaranteed to be non-negative, see, one direction is easy to see. Suppose there were a common 0. At that point, this becomes 0. This is guaranteed to be non-negative. This is plus 1. How can the sum ever be 0? Okay. So if there is a common 0, you will not find multipliers like this. But just as we had in the Nullstellensatz, here also this is a if and only condition. As long as your g's are guaranteed to be non-negative. And the simplest way of guaranteeing non-negativity is to say that's a sum of squares. It's a square or it's a sum of squares. So if I can find g's which are sums of squares and I have multipliers like this, then that gives me a proof that the system is unsatisfiable. Okay, so this is what a proof looks like in SOS. And here's what is known about this proof system versus PCR. In 2018, Christoph Berkholz showed that, maybe this is the journal paper, not the conference paper. 2018, maybe a year or two earlier, over the 0-1 basis, proof size in SOS is not much larger than proof size in PCR. So SOS as a proof system is at least as strong as PCR. Whenever you have short proofs in PCR, you also have short proofs in SOS. But that was over the 0-1 basis. It required a considerable amount of work, although that was done fairly soon, to show an analogous result over the +1 - 1 basis. Over the +1 - 1 basis also, whenever there is a small proof in PCR, there is a small proof in SOS. And the way this was proved was, to say that ideally you want some kind of a size degree relation. And what Sokolov did was this very interesting thing, which said that you take a formula F. Suppose I show you that its SOS proof degree is large. Then I can show that the PCR proof size, not of F, but of F massaged a little bit, composed with some kind of a gadget, that proof size must be large. Okay. So in the 0-1 setting, we directly had degree of F and size of F relation. In the +1 - 1 setting, there is this going back and I go from degree of F in SOS to PCR proof size of F composed with G. I need to go from SOS to PCR and I need to compose with the gadget. And the gadget has to satisfy some nice property. In particular, it could be a majority of 3 bits, some such thing. He had a list of conditions under which this works. So this was shown in 2020. Okay, so this is something that I have mentioned earlier. The non-robustness of PCR. This is folklore, what I mentioned. The handshake lemma is hard over 0-1 encoding, but easy over +1 - encoding. Okay, that is the unsat CNF formula there. And what Sokolov did was to give a way of proving lower bounds for PCR over +1 - 1. So he got these lower bounds for formulas by showing that there were some version of that was hard even in SOS. His lower bounds also are hard over 0. And in 2024, Shashank Mouli, who is also one of my co-authors on this work, he independently showed that the converse of this also holds. There are formulas which are hard over the +1 - 1 basis, but easy over the 0-1 basis. So really, the 0-1 and +1 - 1 basis are incomparable. It's not that one is always better than the other. Okay, so what do we do in the work which I want to talk about?
SOS degrees.
Lower bounds for SOS degree are known.
None.
And those were used by Sokolov to get his proof size lower bounds. Maybe I should. Yeah. So if you have a proof degree lower bound in SOS, you can use that to get a PCR proof size for a related form.
So that is for what kind of form?
So maybe we will come to that.
Okay.
I think we will. If not, then. Okay. Okay, so our first result is this, that you take any so we look at the +1 -1 encoding. Take any formula which is unsatisfiable, whose width is at most d0. So initial CNF is small width. Suppose you know that the PCR, it requires PCR degree D. Okay, suppose somehow you have shown a PCR degree lower bound. Okay, remember degree lower bound is insensitive to whether you are dealing with +1 -1 or 0. +1 -1 or yes. So if you know that it has a PCR degree D, then I will show that the PCR proof size of F composed with G is large. Okay. Now this is different from the previous result by Sokolov in two ways. Sokolov also had something like this, F composed with G, but on this side he did not have PCR degree, he had SOS. And SOS is a stronger system, it's harder to prove degree bounds there. So we show that degree bounds even within PCR can give rise to size lower bounds in PCR over the +1 -1 basis. Yeah, okay, this is contrasting the two. Sokolov's result is only over QR because it went via SOS. SOS is not even defined over other fields because you need this ordering positive, non-positive. Ours works over any field as long as the characteristic is not true. Sokolov's result had this d minus d0 by n square term. So therefore d has to be at least square root. D minus d naught has to be at least square root n. Whereas ours is useful for any d which is greater than the initial. And Sokolov required an SOS degree lower bound. We only require a PCR degree lower bound, which is presumably easier to show. And in particular, therefore, it works for SA, but it also works for SOS.
SOS degree lower bound implies PCR.
Yes. Wait a minute. I'm not completely sure. SOS size lower bound implies PCR size lower bound, but degree, I think degree works. Degree works. Yes. Okay, so
dependence on n, the right hand side. Just
there isn't a dependence on n. Exactly. So there we required this n for the machinery to go up. Here we do not require. Okay, so I hope that the next slide mentions which formula. Yeah, okay. So spin-offs from that theorem, well, for the +1 -1 encoding, we have a simpler proof of separation between PCR and SOS than was earlier. There was a separation known earlier, but this proof is simpler. It's an improved degree to size lift. So what do I mean by a lift? You are taking a degree lower bound and lifting it to a size lower bound. I say lift because size lower bounds are in general harder to prove than degree lower bounds. Okay. For fields with characteristic not equal to 2, you can just take a random 3C, meaning randomly sample clauses of width 3 by picking which variables and what polarity you want them to be. And maybe you need about, with n variables, you need theta n clauses. With high probability, the formula will be unsatisfiable. Aleknovich and Razgorov had shown way back that these formulas will require PCR degree omega n. And our proof says that you take F and you compose it with this indexing gadget. The indexing gadget is very simple. It's a if then else. If A, then B, else C, where A, B, C are individual variables. So for every original variable X, I replace it by a triple of 3 variables. Okay, and that's my composing. So a random formula F of this form requires large PCR degree, and therefore by our theorem, F composed with indexing requires large PCR. And this would be a CNF formula of width 6, not 6, 9. There's a 3 CNF, and then each variable has been replaced by 3, by a combination of 3 variables. In some sense, this was already known, but we are giving a different proof of it. And Sokolov's proof used majority. We are using this index gadget, and it seems to work more nicely. So far, is this okay? Okay, so this was the first theorem. Let me move to the second theorem. So going beyond PCR. Okay. So the outstanding open question in proof complexity is to prove lower bounds for every possible proof system. We don't believe that there is any proof system in which every unsatisfiable formula has polysize proofs. So you give me any proof system, I should be able to somehow come up with a formula which is hard. And there are many proof systems for which we do have lower bounds. So the current threshold, as you can order proof systems in terms of power, the current least powerful proof system for which we do not yet know a lower bound is the system which is called AC0P Frege. So Frege is a proof system which is kind of the textbook logical deduction system. Basically, you have the modus ponens rule. A implies B, then B, and you have some very trivial axioms. A implies B implies C, A implies B implies A implies, and such like. But a small set of 5 or 6 rules comprises the whole system. In that, for the Frege system, of course, we have no lower bounds at all right now. That's like outstandingly open. But one could say, if I have this Frege proof system, and I say that so it's a sequence, it's a derivation of formulas one after another, starting from your initial clauses, you're building together more and more complicated formulas, and finally you produce faults. But suppose I insist that all the intermediate formulas are of small depth. So in particular, in this system, I'm insisting that every formula along the way in the line by line derivation is a polynomial size constant depth formula which uses AND gates, OR gates, negation gates, and mod P gates. Nothing else. Okay? Then we don't know lower bounds. If we throw away the mod P gates and we say what is called AC0 Frege, we do have lower bounds. AC0P Frege, so that is the current frontier for where we do not have lower bounds. And the problem is that mod P gates do not simplify under substitution. I mean, an AND gate, you can set one of the variables to 0 and it goes away. An OR gate, you can set one of the variables to 1 and it goes away. Mod P gates are not easy to kill like this. So even though we have PCR lower bounds, that does not translate to this. PCR, in fact, one of the reasons why PCR was studied so much in depth here was not just to analyze Grosvenor basis algorithms, but in the hope of getting these lower bounds. But it doesn't work. So are there other ways of strengthening PCR so that PCR, the lower bounds in that strengthened version could also give lower bounds? That's one question that people have been asking. So if we think back, how do the lower bounds in PCR, how were they even established? They were established using the size degree relation and separately proving degree lower bounds. So let's look at the size degree relation itself. The size degree relation was proved using this kind of argument. You have a formula F, or you have a polynomial F, and that system with x set to 0, suppose I have a proof of degree d minus 1. In that same system with x equals 1, I have a proof of degree d. I can take these two proofs and patch them together in some nice way to come up with one proof of degree d. In some sense, what we have done here is we have taken this variable x and branched out. And on one branch, you have if you can decrease the degree a little bit, then that is enough leverage to get the patched proof that we want. So one way of adding strength to the PCR system itself is to allow branching on a condition. Instead of branching on a single variable, like is x0 or is x1, I can branch on a condition like this. Is the function of this 0 or is this function of these variables 1? Okay. So now I am going to introduce new variables. These are like, think of them as macros in your LaTeX, So y is a macro, it's a shorthand notation for this. I should introduce macros which have relatively low complexity. I call them extension variables. And I allow branching on an extension variable also. Now can I try and push a size degree relation somehow? So this is what initially it looked like. This is also a no-go. In 2000 already Grigorev has showed that with this you can simulate AC0P. So it's more powerful than AC0P. And Impagliazzo, Mouli, Pitassi, they showed 4 or 5 years ago that it can simulate various other proof systems. It can simulate sum of squares, it can simulate even cutting planes, even TC0 Frege at more or less proportional. So it's too powerful a system. It doesn't matter if you don't know all these terms. The point is that if you make the extension variables powerful enough, then the system goes out of it. So we need to do something more. So we want to add those new macros, but tie your hands and what kind of macros are allowed. And that is what was done in this paper in 2023 over finite fields, mod P fields. There are CNF formulas which have n log n variables initial clauses have width log n. And what they were able to show is that any PCR proof over the field FP, which uses at most n square, well, not even n square, subquadratic. So n raised to 2 minus epsilon. How many macros are you allowed to use? That was a parameter. Subquadratic number of extension variables. And each extension variable is allowed to depend on only log n of my original variables. Therefore, if it depends on only log n of them, it's going to have poly size. If I allow only these many extension variables of only this complexity, even then, these formulas are hard to prove in PCR. They showed explicit formulas like this and proved this lower bound. So this was 2 years ago. And what we did, our second result is improving on this. So here's our theorem 2. For every prime p, there is an unsatisfiable set of polynomials. Again, the same number of variables, n log n, initial degree log n. Every PCR proof over FP using subquadratic extension variables, but each extension variable is allowed now to depend on many more initial variables, as long as its size is polynomial. Meaning the function which describes how it depends on those variables should be computable in poly size. Okay? But much larger arity of these extension variables, even then we can show an exponential size, a lower. So again, there are lots of parameters and lots of this, so maybe we need to see the compare and contrast. Okay, so the previous result and our result. Well, one catch is their lower bound was for polynomial systems which came from CNF formulas. Ours is for polynomial systems which come from AC0P formulas. So we can write down these polynomials, but if you try to write the CNF encoding which would give rise to these polynomials, that CNF encoding itself is too large. But instead of individual clauses, you think of a CNF formula as a bunch of constraints where each constraint is a clause. If I instead allow writing each constraint as an AC0P formula instead of a clause, then these are small formulas. So in that sense, our result is weaker. But in the second line, our result is much stronger. The previous result allowed only each extension variable to look at only a log n sized window of the original variables, whereas we are allowing an n to the 1 minus epsilon window. Extension size is the same in both cases. In our case, we had to explicitly say that this is the extension size. In this case, it was not even necessary to say it because the arity already implied. Okay, so these are our two main results, and I have two more slides which are telling you what are the key ideas in each of these results, but they are already over time. So, and I can spend a couple of minutes on each slide, or I can just completely skip it. What do you? I can continue. Okay, I'll try to keep it very short. Anyway, I have only one slide for this. So the key ideas in the proof of theorem 1. Theorem 1 was saying that over +1 -1 encoding, we have a simpler proof which lifts PCR degree to PCR size. And how did Sokolov do this? Sokolov, remember, he lifted SOS degree to PCR size. But how he did it was, his key observation was that degree is not representative of size. The moment you go over to +1 -1, degree is not the right measure. But what is a useful measure is quadratic degree. And what is quadratic degree? You take a line in your proof, a polynomial, and you take two monomials in that polynomial and you multiply them. That would be a new monomial and its degree. So the degree of terms of the form T1, T2, where T1 and T2 both are appearing in the same polynomial in some line in the. So this is a completely different measure. And this is not just the degree of D1, D2, because you are also going modulo the Boolean ideal. So all x squares go away. Right? X square is equal to 1 in this setting. So his key observation was that quadratic degree is much more representative of size. Why is it representative of size? In a line xp1 plus p0, take a line in which some monomials have x and some monomials don't have x. Where all can x contribute to the quadratic degree? For it to contribute to quadratic degree, you should take one monomial from p1 and one from p0. That's the only way you will actually get x contributing to this. So what you can do is you can take that entire proof that was given to you and split it in such a way that you are separately computing P1 and P0. Instead of computing x P1 plus P0, you separately compute only P1 and only P0 and put it together. So it removes the interaction of terms where x is contributing. And then you show that the degree lower bound can be preserved using this. This is what Sokolov did. So he did not have to set any x to 0. It was crucial. And this is what he did. So now what did we have to do? we used ideas from a older paper with this indexing gadget, but we still use this split. We split on carefully chosen variables. So we use the indexing gadget. The indexing gadget says that this is a selector variable. If this is 0, then take this. If this is 1, take this. Now, I take my original formula, compose it with this. The moment you set all the W zeros, in any one triple, the moment I set W0, one of these two becomes irrelevant. Because if this is 0, then W2 is irrelevant. If this is 1, this is it. So half the remaining variables become irrelevant the moment I set the W's. So what we do is we very carefully choose a setting to the W's which kills quadratic degree terms and makes many variables redundant. And then once the variable is redundant, you use that variable to split the proof. So of course, there's a lot of more technical machinery which has to be done here, but essentially this is the idea that instead of degree, focus on quadratic degree, focus on variables which are already made irrelevant. How do you choose which variables are relevant? By using some kind of an indexing gadget and a carefully chosen restriction. So this was really the main idea in our first result. In our second result, the hard formula, the formula for which we proved the lower bound, was some kind of a generalized pigeonhole principle formula. For proof complexity people, pigeonhole principle is very dear to our hearts. So the pigeonhole principle is simply saying that n+1 pigeons cannot go into n holes without collision. You write this down as a CNF, and there are all kinds of proof systems where you write a negation of this, that there is a way of sending n+1 pigeons into n holes without collisions. And all kinds of proof systems, this seemingly blatant falseness is hard to prove. So it clearly is showing that there is something very limited about these proof systems. They can't even prove that this negation of the pigeonhole principle cannot be satisfied. And then there are many variants of the pigeonhole principle. I mean, how many more pigeons than holes do you need until it becomes easy? Because if there are m pigeons and only n holes, it will be easier to show that there must be a collision. There's just one more, maybe it's harder. Or if I say that, okay, not only do I want a map from pigeons, assignment of pigeons to holes, it should be functional, it should be onto. All kinds of variants we have looked at in various different settings. And there are lots of hardness results. There are lots of separations. Some variant is hard here, but easy there. So for comparing proof systems, pigeonhole principle is super useful. Way back in 1998, Rasborov had defined a more complicated generalized pigeonhole principle. So instead of saying that so the pigeonhole principle you can think of as a bipartite graph. You have these n+1 pigeons here, n pigeons here, and edges saying which pigeon can go into which hole. And then maybe the graph need not be the complete bipartite graph. It could be a limited graph. These pigeons can only go into holes where they are connected. But Rasborov defined this generalized pigeonhole principle formula, which was even more weird. So there was the left-hand side, which were fractional pigeons. So some n things on the left and n things on the right. And each, there are some edges saying what can go where. And a pigeon is a combination of a certain number of things from them. So if all of them go to the same hole, then you can say that that pigeon has gone to the hole. So that's why I called it a generalized pigeonhole principle formula. I have no idea how we came up with this definition in the first place. But having come up with it, he was able to give lower bounds for it. And what we do is we take that formula, the generalized pigeonhole principle formula, and we compose it with XOR. So because we compose it with XOR, now it no longer becomes easy to represent in CNF. Because if I have K things and then I do a XOR of them, then you will have a parity of those many variables, which requires large loop. So the strategy is again a bit reminiscent of what we did in the previous theorem. You find some variable which appears in many high quadratic degree terms. So we again look at quadratic degree. If you find a variable which appears in many quadratic degree terms, try to set it. Remember, now we are not over the +1, -1 field. We are over the finite field. So you want to set that variable and kill all these quadratic degree terms. Set it to 0. Unfortunately, that variable which is appearing in many high quadratic degree terms, maybe you are not even at liberty to set it to 0. If it's an original variable, yes, you can set it to 0, you get a restriction, but it might be an extension variable. And it might be an extension variable for which on every setting of the original variables, it takes a non-zero value. So then you can't even set it to 0. So then we have to do a lot more work to find a partial assignment, which maybe doesn't set it to 0, but at least makes that extension variable linear. And if it makes it linear, because I've restricted some of the variables, then I can do a split on this. So again, the technical machinery in this proof is to carefully choose how to kill many high quadratic degree terms. So quadratic degree is still useful. Extension variables require special handling. And once we figure this out, how to bring extension variable to small linear form, we again do the splitting of a proof into the part which is independent of x and the part which has x. And having done this, we have applied a restriction. We should make sure that the resulting formula after you apply the restriction is still an instance of generalized vision. Because then we want to use an inductive argument. Right? I started with these many variables, I restricted some of them, I did some work to convert my proof, and now I still have a proof of a smaller instance of the same form. So some cleanup would need to be done, and our cleanup is a little bit more efficient than what was done. So a lot of technical details which are there in the paper, but I hope at a high level I have conveyed what we need to do. Because as I promised, the key ideas I've ended there, and here's a summary. So what did we show? We showed that for fields which are not of characteristic 2 plus 1 minus 1 encoding, we have a degree to size lift for PCR. Earlier, there was only a SOS degree to PCR size. Now we have a PCR degree to PCR size. And over finite fields, with the limited use of extension variables, we have a size lower bound, which was better than what was known earlier. In both these proofs, a crucial idea was to use quadratic degree and to split it. And in some sense, both of these ideas were there in earlier work, but the way they were put together in this work wasn't. So what is still open? Lower bounds for CNF formulas in PCR over finite fields. This is our proof was for that generalized pigeonhole formula composed with XOR. So we have been asked time and again, can't to give me a CNF formula which is hard with the same number of extension variables. We still don't know how to prove it. We're still trying. Maybe we will succeed. The current formula which we are trying is also a version of pigeonhole. We are not going very far away from pigeonhole. One could also ask about lower bounds with other encodings in PCR. Like I said, the main thing is that you choose two different values to encode true and false. So 0 and 1 is the normal setting. Plus 1 minus 1 is also a very natural setting because that's what is used in Fourier analysis. But I could fix a finite field. For instance, I could fix my field to be F5 and then I say I encode true as 1 and false as 4. Or that would be 1 minus 1. So 1 and 3. I choose something like this. So two distinct non-zero values. As of now, we don't know how to prove lower bounds, even for this set. For proofs in this set. And of course, this is the outstanding open problem currently in proof complexity. Lower bounds for the AC0P Frege system. Okay, so with this, I'll stop. Thank you very much for listening.
So are there any questions?
About to ask the same question. So this quadratic degree idea works in the plus 1 minus 1 basis, I think, right? Not two distinct non-zero values.
It doesn't seem to work over the two or arbitrary distinct values. Well, going from 0, 1 to any two non-zero values would also be an affine shift.
Right.
But we are using two properties of plus 1 minus. One is that it's an affine shift of 0, 1, and the other is that multiplication can be inverted because x square is 1. No? So you multiply by x in the polynomial calculus, you can again multiply by x and nullify that. So over a finite field, this should still be possible. I mean,
Yeah, cyclic structure is.
yeah, but I think we have not yet figured out how to do this. So this is what Sokolov also said, is he believes is the current boundary.
What question of curiosity? Say this or this is a P private. No non-trivial lower bound is not. I mean, I'm not talking about exponential lower bound. Like
No. So we do have circuit lower bounds for AC0P. For instance, we know that in AC0P kind of circuits cannot compute mod Q if P and Q are co-prime. AC0P circuits are circuits of constant depth polysize with mod P gates, and they cannot compute mod Q. This is not useful. So a circuit lower bound is not necessarily a proof complexity law. And so for AC0P Frege, we know nothing. It was expected that automatically these proofs were so. But once we had the AC0 lower bound for parity, which was proved using a kind of switching lemma, The AC0 Frege lower bound also used a switching lemma, but a tweaked version of that. But it did not work beyond AC0.
So if there are no further questions, let's have a speaker.
Thank you.
Here's a actor from
Thank you so much.